In the previous class, we have studied the working of helium neon lasers and some of its applications. Let us now turn our attention to ion lasers. This is the second variety of gas lasers. We now know that atomic gas lasers are capable of generating light. We now know that the atomic lasers are capable of generating light across visible and near-infrared region of the electromagnetic spectrum and not capable of generating light of shorter wavelength, that is in the ultraviolet region. So basically, what is that? The atomic gas lasers, if this is the wavelength, it uses this direction. So this is visible, this is infrared, and this is ultraviolet. So atomic gas lasers, we now know, can generate light spanning across visible and near infrared, only some part of the infrared spectrum. And they are incapable of generating light even visible short wavelength visible. Even in this region, they cannot emit coherent light, provide coherent light. That is simply because here, atomic gas lasers, the electrons involved in the lasing transition are essentially the valence or outermost electrons for the generation of light of shorter wavelength, at the shorter end of the visible and into infrared, ultraviolet, and even beyond. Clearly, the inner electrons, which are more strongly bound to the nucleus, are to be engaged in the process of lasing. You see, if the electron is bound more strongly with the nucleus, then you need more energy to take it to an excited state. So the excited states would be separated by higher energy, and therefore the transition between them also would yield light of shorter wavelength. So I think you have understood this. And how can you do that? How can you involve electrons which are closer to the nucleus, that is bound more strongly in the nucleus? You'll have to basically strip the outermost electron or electrons from a neutral atom. That means the active species of these ion lasers will have to be ion and not neutral atom. That is why they are called ion lasers. This realization led to the first observation of laser action in gaseous ions by William Earl Bell in early 1964, not long after the discovery of lasing in atomic and molecular gases. He actually basically used singly ionized mercury atom to demonstrate the very first operation of an ion laser. I would like to mention here that the research work of William Bell also led to the development of first atomic clock. Of course, it has no connection with the operation of lasers. I just wanted to mention to you. This was used in the Apollo missions to the moon. The atomic clock that he made is now on display along with his handwritten notes in the Smithsonian Museum of American History. You may be knowing that an atomic clock is an extremely accurate type of clock which is regulated, the time of which is regulated by the vibrations of atomic or molecular systems. If you know the time of vibration, you can of course translate it into the actual time. So it basically helps you to measure time almost without any error. And such accurate measurement of time is indeed very important for space mission like the one that took place on the moon many decades ago. And by the end of 1964, laser action was reported in the ions of 11 gases that resulted in the addition of 200 more wavelengths to the rapidly growing list of new lasers at that time. As you know, at that time there was a concentrated activity to obtain coherent light at newer and newer wavelengths. And argon ion laser and an ion laser made a great impact because this, for the first time, produced coherent light at ultraviolet wavelengths. Before the advent of ion lasers, the coherent light was possible to be emitted only over the infrared, near infrared, and some part of the visible. That's all. Similar to most atomic and molecular gas lasers, ion lasers are also pumped by taking advantage of gas discharge. That is, basically, you have closed your gas in a discharge tube, you apply voltage, create electrons, beginning, of course, from the stray electrons, which is intrinsically present. And then these electrons actually, you basically translate the energy that is drawn from the line as kinetic energy, transfer that energy to the electron as its kinetic energy, and that energy eventually will give you coherent light. We know that. However, unlike the atomic gas lasers, energy needs to be expended to form an ion by stripping an atom of its electron. You have to spend more energy here to create your active species, that is, light emitting species, which are not neutral atom anymore. You have to strip the atoms of their electron and create ion, which will be your active species, light emitting species. Therefore, the kinetic energy of the electron supplies this ionizing energy as they collide with the neutral atom. So, basically what happens, you have the neutral atom and it collides with electron, which has kinetic energy in the discharge. It has acquired this energy from the energy that has been tapped from the line, and this will actually ionize the atom and will create another electron in the process, and this electron will move with less kinetic. So this is very essential to create your active species. This is now your active species. You have to create them in large numbers. The energy required to transfer a fraction of these ions to the upper laser level for establishing population inversion also is provided by the kinetic energy of the electron as they undergo inelastic collision with the ions. Now, once the ions have been created, they will have to be pumped to the pump level and for realization of population inversion. So then, how do you do that? Once again, you take advantage of collisions with electron. This time it is inelastic. So it collides with electron, which has its kinetic energy anyway. So it will excite the atom to its excited state. And the electron will supply that energy and it will move with less kinetic energy. So here, first you create the active ions, active species, then the active species will again collide with electron, inelastic collision, and you will then create excited state and eventually realize population inversion, prerequisite for the process of lasing. The ion lasers therefore are able to convert only a tiny fraction of the pump energy into the creation of coherent light. Therefore, its efficiency will be much lower. I cannot say much lower, but would be definitely lower than that of atomic gas lasers. As a matter of fact, the efficiency of ion lasers is much lower than the gas lasers, atomic gas lasers. And generation of lasing in deep ultraviolet requires doubly ionized ions. If you have to reduce the wavelength of the light that will be emitted, that means if you want to go to the deep, then you will need the electron to be bound with the nucleus even more strongly, so that you need to expend more energy to take the electron, to excite the electron, so that the separation of energy levels of the electron is even more. Energy levels are separated by even more energy, so that the emission between these levels will give you light of even shorter wave. And therefore, this laser, which will give you deep UV ones, which would require doubly ionized ion, will have even poorer efficiency, because you see, you need to exert more energy, because you have created first a singly ionized ion, and then you will have to strip another electron from this ion. So it will again collide with electron, and this electron will strip another electron from it. So this is now doubly ionized. So you'll have to impart more energy to create this active species. This is now the light emitting species. So, and then this will collide with electron, and E will now generate, take it to the excited state to create population inversion. Therefore, such lasers will have even poorer efficiency. It is not surprising that wall plug efficiency of ion lasers can be as low as 0.001%, and they typically lie within 0.01% to 0.001%. Suppose for the operation of such a laser, whose efficiency is 0.001%, we use a pump power of say 100 watt. So you will, from 100 watt, you will at 0.001% efficiency, you will produce 0.0. So it is not surprising that the wall plug efficiency of ion lasers can be as low as 0.001% and typically lies within 0.01% to 0.001%. Let us assume that such a laser which operates at 0.01%. And suppose our input power, that is the power we draw from the line, is 100 watt. Therefore, at 0.0%, 1% efficiency, this laser will produce coherent light of power which will be just 10 milliwatt. Just imagine, you are drawing 100 watt and you are producing coherent light whose power is just 1 milliwatt. Incredibly low operating efficiency. So why do you at all go for such laser? That is because you are creating coherent UV light which have some important applications, and this light cannot be produced by most of the other lasers, and that is why you go for it. Well, let us now turn our attention with this general introduction to ion lasers. Let us now turn our attention to the working of argon ion laser, which is regarded as one of the most popular and important ion. The argon ion laser was first operated in 1964 by William Bridges at the Hughes Aircraft Laboratory soon after the invention of this class of lasers by William R. Bell when he first operated ion laser by making use of singly ionized mercury atoms. Argon ion laser is the most powerful continuously working laser in the ultraviolet range. It can actually produce tens of watts of output in conventional operation. See, if it has to produce tens of watts of output, and if the operating efficiency is low, you can imagine how much power is being drawn from the line. The most popular wavelengths that can be obtained from argon ion laser are 450 nanometer, that is blue light, 488 nanometers blue-green light, 500 nanometer green light, and 351 nanometer, which is the ultraviolet region, lies in the ultraviolet region. And because more heat is dissipated in an ion laser compared to the other gas lasers, other gas discharge lasers, it is well known. And because of this, actually, ceramic discharge tube is often used for the operation of an argon ion laser instead of quartz tube, because with a quartz tube, it would be quite challenging to manage such huge dissipation of heat. That's why a ceramic discharge tube is often used for the operation of argon ion laser. The basic construction features are qualitatively similar to other low pressure gas discharge tubes. The high power argon ion lasers, however, have a solenoid spiraling around the discharge tube, because you basically will have to increase the density of current, because you will have to create the ions. You need many more electrons compared to the operation of a conventional atomic gas laser. Now, how do you do that? And if you have to generate high power, you have to create that many more argon ions. So how it is done? Actually, the discharge tube a electromagnetic coil is wound around it, and as the current flows through it, it produces axial magnetic field. This actually confines the electrons and also ions near to the center and would not allow the ion to move near to the wall. So this maintains very high density of current density, that is high density of electrons, which facilitates the high power operation of the argon ion laser. So this electromagnetic coil wound across the plasma tube generates a strong magnetic field longitudinally along its axis, as I said. This essentially increases the current density by keeping the electrons and ions near the center, rather than allowing them to collide with the wall of the discharge tube. The better confinement of plasma, in turn, allows scaling up of the power. That is because how you are scaling up, you are increasing the number of light emitting species, which here is argon ion, and is particularly useful for UV emission that have inherently low power conversion efficiency, The outer wall of the discharge tube of a low power laser, whose power lies below 100 watt, is air cooled. It is cooled with air. If the power of the laser is less than 100, the dissipated power can be cooled simply by flow of air. But as the power increases, it becomes far too hot and is required to be water cooled, often by incorporating a recirculating cooling system containing a chiller. You'll have to remove heat at a faster rate. So air cooling would not suffice. We'll have to force cool with water and taking advantage of a chiller system. See, a part of the kinetic energy of the electron, as we know, is expended in ionizing the atoms, and another part is spent in raising the ions to higher energy levels. We have already discussed this. And there exist a number of metastable states to which the excited ion can drop down. See, I very qualitatively explain you the energy level diagram of this laser. This is quite complex, and I would not go into very much deeper into the energy level diagram. I will make a very qualitative representation. See, this is your ground state of argon. So as it collides, argon ion, it collides with electron and it climbs up to its excited state. So you take it out. This is the pump level. From here, it can drop down to a number of metastable states which perform as the upper laser level. And then you have the lower laser level, and then from there it can actually relax to the ground state. This is very qualitative description. So these, once you pump, they actually drop down to any of these metastases. They are all metastable. So population can reside in these states for relatively longer time. And transition, this is the lower laser level. Transition between these will give out your lasing emission, and that can occur at number of wavelengths. Say this is lambda 1, lambda 2, lambda 3, and there can be even more than that. So if you use a non-dispersive cavity, that is the cavity where there is no wavelength selection element, wavelength discriminating element, then the laser, you have the glow discharge because it is low pressure, the discharge is filling the entire volume. Then this is your back mirror, and if you remember, this is a Brewster window. If you put a Brewster window, then by exploiting the polarization dependent reflectivity of a Brewster plate, you can actually generate polarized light. So if you put Brewster window, automatically the laser will give out polarized light. We have already studied. Now, if there is no wavelength selection element inside the cavity, then as you have created population inversion, the spontaneous emission will occur on all these wavelengths, and these will speed stimulated emission in this active medium. And so light will grow on all these three wavelengths, that is lambda 1, lambda 2, and lambda 3, which I showed. So the emission of the laser, because all these wavelengths can oscillate back and forth inside the cavity, they will be amplified as they travel through the gain medium, and therefore the lasing would also occur on all these three wavelengths. How can you verify it? You actually shine this emission of the laser on a prism. Prism will split this into their into their all individual wavelength component spatially. Therefore, different wavelength will now be spatially separated, and so you can see that this would give this multi-line output, multi-wavelength output, because there is no wavelength selection element. So the laser will emit on multiple wavelengths. Now, you use a dispersive cavity. That means you now bring that prism which was outside inside the cavity. So what happens now? You once again have created gain on all these three wavelengths, and spontaneous emission will begin on these three wavelengths, and stimulated emission will be seeded by that. However, as these three wavelengths shines on this prism, prism will split them. This is lambda 1, lambda 2, lambda 3. And only one of these wavelengths will fall normally on this mirror, and therefore this alone would be able to reflect back, and we will be able to oscillate back and forth inside the cavity, and would be able to extract energy from this gain medium and would be amplified. The other wavelengths, that is lambda 2 and lambda 3, will fall obliquely on this, and this, as you can see, it is not even intercepted by this output. So there is no question of oscillation on these wavelengths. So this way, by using this intracavity prism, you can make the laser emit on single wavelength. And by tuning this mirror, if you tune this, suppose we make it like this. This is now my output. So as you can see, this wavelength is not falling normally on this. So there will be lambda 2 will now oscillate, and lambda 1 will be just fly off. So by tuning this mirror, or even by tuning this grating, this prism, either this mirror or this, you can choose different wavelengths and make the laser oscillate on those different wavelengths. So I think I'll stop here today, and tomorrow we'll begin from here.